complex numbers, quadratic equations. So we remember from algebra that if we have a quadratic equation, that it generally will cut the x-axis twice, and where it cuts the x-axis represents the roots of the quadratic equation. So in the first graph here, we can see that the quadratic equation cuts the x-axis twice, so we say that the function has two real roots. In the second graph, we can see that it just touches the x-axis, so in this case we say that it has a repeated root, or it has one real root. And the third graph does not touch the x-axis at all. So in that case, we said that it had imaginary roots. And we know from our minus b formula that the part of this equation that represents the roots, or is called the discriminant or the determinant, well, in the first graph, we know that b squared minus 4ac has to be greater than 0. In the second graph, b squared minus 4ac equals 0. And in the third graph, b squared minus 4ac is less than 0. So this means that when b squared minus 4ac is less than 0, that the roots of the quadratic equation have to be complex roots, so that we can deal with this square root of a negative number. So if, for instance, we're asked to solve this quadratic equation, instead of seeing x's in it, we're going to see z's, because we're going to be dealing with complex roots, and we treat it exactly the same as any other quadratic equation. But what we'll notice is that we will never be able to factorize. In other words, we will never be able to find a number that multiplies to give us 13 and add to give us minus 6. So instead, when we can't find factors that way, we will always look at taking the coefficients of z squared, which is a, in other words 1 in this case, the coefficient of z, which is b, in other words minus 6 in this case, and then the constant, which is c, so 13 in this case. So if we sub that into our minus b formula, well, we have minus times minus 6 plus or minus the square root of minus 6 squared minus 4 times a times c, all divided by 2 times a. So on the top, what that simplifies to is 6 plus or minus the square root of 36 minus 52 divided by 2. And underneath the square root sign, then that simplifies to the square root of minus 16. And of course, we can't get the square root of a negative number, so instead we write that as the square root of 16 times the square root of minus 1. And we know the square root of 16 is 4, and the square root of minus 1 we write as I. So that means that our two roots then are 6 divided by 2, which is 3, and 4i divided by 2, which is 2i. Now, if we look closely at these two roots, and I separate them out, what you'll actually notice is that one is a complex number, 3 plus 2i, and the second is the conjugate, 3 minus 2i. And if I go back to the original quadratic, we'll see that the coefficients of z squared, z, and the constant, they were all real coefficients. So 1, minus 6, and 13 are real coefficients. So when we have real coefficients, what this means is that we will always end up with our complex roots as a conjugate pair. So we want to make sure that we remember that, because that's going to come in useful. So this one comes up less often, where we can see that the coefficients are not real. So in other words, the coefficient of z squared is 1. The coefficient of b is minus, be careful of the minus there, and 1 plus 4i. And then c is 2i minus 4. So because there's i's here, then we say these are not real coefficients. So let's see what happens when we go and use our minus b formula. So we'll have z is equal to minus 1 plus 4i plus or minus the square root of b squared. And if I look at b, I'm just going to simplify that there before I put in b squared. So that's going to be minus 1 minus 4i squared. And then minus 4 times a times c all over 2 times a. So that gives me minus minus, so just simply 1 plus 4i. And then underneath the square root sign, I have minus 1 squared, which is 1. Minus 1 times minus 4i is 4i. And if I double that, that gives me 8i. And then minus 4i squared is 16i squared. Minus 4 times 1 times 2i is minus 8i. And minus 4 times 1 times minus 4 is plus 16. And then that's all over 2. So simplifying underneath the square root sign then, remembering that I squared is always equal to minus 1. Well, that gives me 1 plus 8i minus 16 minus 8i plus 16, which is great because we're going to get a couple of things cancelling here. The 8i and the minus 8i is 0, minus 16 and plus 16 is 0, and therefore that leaves me with then 1 plus 4i plus or minus the square root of 1, which is just 1, all over 2. So in other words, my two roots are simply 1 plus 4i plus 1 over 2, or 1 plus 4i minus 1 over 2, and that gives me 2 plus 4i over 2. And if I divide everything by 2, that gives me 1 plus 2i as my first root. And then my second root, well, 1 minus 1 is just 0, so I'm left with 4i divided by 2, and 4i divided by 2 is 2i. So this time we see when the coefficients are real, the roots are not a conjugate pair. So it's important to notice the difference between the two. So when there's i's, when we do the a, b, and c, then we're going to have two completely different roots, no relationship whatsoever. And when the coefficients are real, so no i's for a, b, and c, then we will always end up with a conjugate pair in our answer. So if we call those examples type 1, where we're solving our quadratics, then the second type that we want to look at today is where we're going to go in reverse, where we're going to form the quadratic. So this is no different from algebra. So if we're given our roots, we can write out the factors and then we can multiply our factors and get our quadratic. But of course we have our nice shortcut formula that if I have my quadratic and I want to form it, remembering that this is complex numbers, so we're going to write it in terms of z and not x. So it'll be z squared minus z times the sum of the roots plus the product of the roots. And because it's an equation, then we say equal to 0. So that means if I know my two roots, then I can simply sub it in and I'll have my quadratic. So say, for instance, here, if I have two roots, 6 plus 4i, I can see it's a conjugate pair. So that means that when I form my quadratic, there will be no I terms in my quadratic. So I say z squared minus z times the sum of the roots. Well, one of the roots is 6 plus 4i and 6 minus 4i. So I add the two together. And then I'm going to multiply my roots. So 6 plus 4i times 6 minus 4i. So if I simplify what's in the brackets, I have 6 and 6 is 12, and 4i minus 4i is 0. And then multiplying out my brackets, I have 6 by 6 is 36. 6 times minus 4i is minus 24i, 4i by 6 is plus 24i, and 4i by minus 4i is minus 16i squared. So again, we always remember I squared is minus 1, which will always be given to us in the leave insert. So simplifying that out, we have minus 12z, and then we have 24 minus 24 is 0. And of course, then we have 36 minus 16i squared. Well, minus 16 times minus 1 is going to become plus 16. So that gives me z squared minus 12z plus 52 equals 0. Okay, so let's have a look at some questions then. So if we go to our active maths textbook, and we're going to go to page 297, and we're going to mark the following questions. So question 2, part 6, question 4, question 9, question 10, part 4, question 11, part 2, part 7, question 12, part 1, part 5, and question 13, part 2.